Hello guys, welcome to Ramta Solutions and welcome to your grade 12 Physical Sciences. We are still continuing with momentum and impulse. Today we are looking at conservation of momentum. So this video, as is usual, we're going to introduce the reasons why we are introducing this, or we are dealing with conservation of momentum. We are going to also talk briefly on Newton's third law of motion, which basically brings about the law of conservation of linear momentum. And lastly, we will have worked examples of this topic. Okay, at the end of this video, you must be able to use this formula that you're seeing here. Okay, so without any waste of time, let's get into it. Now, for introduction and revision, let me remind you, we have said momentum P has the formula P equals mv. And we have said change in momentum, we have said change in momentum delta P has the formula delta P equals mass multiplied by difference of change in difference of velocity, meaning final velocity minus initial velocity. And then we also talked about Newton's second law of motion, cos Newton's second law and momentum. And we also talked of Newton's second law and momentum, which gave us the formula F net is equal to change in momentum over time, or over change in time, right? So these are formulas that we're going to use. So look at this and remind yourselves what we were doing in these 3 videos. Okay. All right. Now, sorry. So now for the video that we are dealing with, the current video, we will say, 1, imagine the collision of 2 objects. All right. Imagine the collision of 2 objects with different momentums, of 2 objects with similar or different momentums, because it can be similar as well. That's all. I shouldn't be saying different, right? I mean, with similar or different momentums. All right. So this is what we are going to look at today. Basically, this is what we are going to look at, and we are going to investigate and quantify this situation. Okay. So without any waste of time, let's get to the second point. Let's remind you, you are now in grade 12. Let's remind you, we also did Newton's third law of motion. We're only going to talk about it briefly. Newton's third law of motion. And in fact, we're not going to talk about it briefly because it'll lead to something special. Okay. If you recall, Newton's third law of motion said, maybe let me insert something here. Yes. Let me insert this here. Oh, yeah. Okay, so that the whiteboard can be visible, let me change the background. Okay, I'm going to change the background for this slide only. Okay, so now we talk Newton's third law of motion. Okay, we're talking Newton's third law of motion. So Newton's third law of motion says if body A exerts a force on body B or body B, then body B exerts a force of equal magnitude and of equal magnitude on body A, but in the opposite direction. Okay, but in the opposite direction. So, but in the opposite direction. Okay, so I want to say, let's maybe call our object A, and let's call it B. Okay, so this is what we need. So that law says if body A exerts a force on body B, then body B exerts a force of equal magnitude on body A, but in the opposite direction. In the opposite direction. Sorry about that. In the opposite direction. So in the opposite direction. And in the opposite direction. Okay. In the opposite direction. So mathematically, we represent this as F sub A would be equal to negative F sub B. All right. So this is Newton's third law of motion. So I repeat, the law says if body A exerts a force on body B, then body B exerts a force of equal magnitude on body A, but in the opposite direction. So by saying in the opposite direction, hence we have A negative B. Okay, hence we have A negative B. Okay, so we, as you have seen here, we have considered, maybe let me proceed in the next. So now consider the collision between two billiard balls. Okay, consider the collision between two billiard balls. By the way, guys, remember, this collision could be of multiple objects, not only two, it can be more than two, but we will restrict it to two just for simplification, okay? Consider the collision between two billiard balls. And then again, we must also consider the system to be isolated. Okay, consider this system to be isolated. Okay, consider the system to be isolated. What do we mean by that? We mean the F net is 0, and we basically what we want is this. We don't want any external force, okay? So consider the system to be isolated. To be isolated. All right, let me underline here isolated. So when we talk isolated system, I'm going to give you a definition which is very important for your exam. I'm going to give you a definition which is very important for your exam. Isolated system is a system in which the resultant force is 0. Okay. A system in which the resultant force is 0. Right? A system in which the resultant force is 0. Okay. That is your definition of an isolated system. Okay. That is your definition of an isolated system. Let me check something. I think, do I have a highlighter? Oh, I don't have a highlighter here. Okay. So that is the definition of an isolated system. Now, again, you're considering the collision between two billiard balls, like we had in the previous page, we have said the force that body A exerts on body B is equal to the force that object B exerts on body B in magnitude on body A, in magnitude, but it is opposite in direction. I repeat, so we said f sub A is equal to negative f sub B. So we're saying the net force is 0. So this f of A will be the force applied by object A. If you recall, we have said in previously, F net is equal to, because it's a comment here, let me change the color. We have said F net, I think yellow would do. We have said F net is equal to delta P over delta T. All right, we have said that F net is equal to delta P over delta T. So here, we're going to reuse this formula, but instead of net, I'm going to just write f of A. So f of A, of course, instead of net is f of A. So what does it mean? It means f of A is tangent P of A over delta T is equal to negative tangent P of object B all over delta T. In other words, this is Newton's second law of motion. We are using it now, right? All right. Now that we have used it, let's proceed. Let's proceed. It'll be proceeding. It'll be, as you can see here, that we can now cancel the times. So basically, we will be left with tangent momentum of object A is equal to negative tangent momentum of object B. You recall, tangent momentum was momentum of A final minus momentum of A initial. In the same way, tangent momentum of object B was momentum of object B initial plus also the final minus momentum of object B initial. Right? Further algebraic manipulation, we have negative times negative is negative, so it's negative PP, negative momentum of object B final, negative times negative is positive. We have positive momentum of object B initial. All right? Perfect. So as you can see, this final momentum is negative. How about I transpose it to the other side? It'll be momentum of object A final plus momentum of object B final is equal to momentum of object A initial plus momentum of object B initial. Can you see that? All these, basically we refer to them as total momentum final is equal to total momentum initial. Okay. Total momentum final is equal to total momentum initial. In physical sciences, whenever you see final is equal to initial, it'll lead you to conservation of something. Okay. It'll lead you to conservation of something. Okay. It'll lead you to conservation of something. Now, that being said, it means we must now move on to, oh, by the way, we're only going to stop it here. Okay, but we are moving on to the third point. Now, the third point that we have to address is, how did we put it? We said it's law of conservation of linear momentum, right? It's the law of conservation. So it's the law of conservation of linear momentum. Right, it's the law of conservation of linear momentum. So from Newton's third law of motion, let me write that right there. From Newton's third law of motion, we got total momentum final is equal to total momentum initial. If you like, you can also write this as M sub A final plus M sub B final is equal to M sub A initial plus M sub B initial, right? Even whether you start with initial on the left and final on the right, it doesn't matter. It's the same thing. Okay, so this is the law of conservation of linear momentum. Okay, this is the law of conservation of linear momentum. Okay, what is this? I'm basically referring to this. Whether you take it as this part here or this part here, it doesn't matter. Okay, this is the law of conservation of linear momentum. Now, in weights, what is that law saying? In weights, it says, total, okay, let me write it like this, the law of conservation, let me begin like this, the law of conservation of linear momentum states, well, but the state is not something that you must write. Okay, state the total linear momentum, of an isolated system is constant. Okay, or is constant. Okay, remains constant is fine. Can also say remains constant. The total conservation of the total linear momentum of an isolated system remains constant. If you don't want to use this part of remains constant, you can say is conserved. Okay, so in other words, you can say the total linear momentum of an isolated system is conserved. Or instead of saying is conserved, you can say remains constant. Okay, you can say remains constant. Okay, I need to go back to a point somewhere that I want to highlight. We said an isolated system is a system in which the resultant force is zero. Remember, when we talk resultant force, we're talking the sum of forces, right? So let's go. So this is me. Let me write in red. Is the system isolated? I think I should bring this point. Is the system isolated? The answer is, let's see. F sub A is equal to negative F sub B. What is this? F sub A plus F sub B is equal to 0. So what is this? We can call this one the total forces. So the net force, it's equal to 0. So what is our answer? Our answer is yes. Right? Our answer is yes. Right? So because this was a comment that I think I was supposed to have done earlier, and then we just put it in a block like this. So yes, indeed, the system is isolated. As you can see, the net force is equal to 0. Alright, so remember, with this net force, we're basically summing all individual forces that are acting on in the system. Alright, so yes, indeed, it was 0. Okay? Alright. Now, moving on. We said the law of conservation of linear momentum says the total linear momentum of an isolated system remains constant. Alright? Remains constant. And this is the law. Whether you write it like this or you write it like this, it doesn't matter. Okay, so let me just write the law. The law is, I'm going to begin with initial press is equal to, oh boy, Now I have forgotten the MV. We can't have initial mass, VAI plus MB VBI is equal to MA VA final plus MB VBF. So this is the law of conservation of this is the law of conservation of linear momentum. Right? This is the law of conservation of linear momentum. The law of conservation of linear momentum. So mathematically, this is how we represent the law. Okay. Mathematically, this is how we represent the law. If you like, you will find, especially in your textbook, it can be M sub 1, V sub 1, I. It says mass of object 1, mass of object 2, it'll be, instead of A and B, it'll be 1 and 2. It doesn't matter, guys. Sometimes you even change it to track and blah, blah, but because those can be weights that are too long, we just use your A and B or your 1 and 2. Okay, but preferably your past paper, the formula in your past papers, in your exam papers, they use M1, M2. It's okay. There's nothing wrong with it. It's super perfect, okay? Because it simplifies things for us, okay? All right. But we are going to use M1, M2 when we deal with a section of past papers, because there will be a video in the end of the series, okay? So we know what these things mean. Okay. Now we are going to, where should we go? We are going to the fourth section, which is wet examples. I think we are going to try 2 wet examples. And because this is now deep into the topic, we are going to use one past paper question. Yes. We are going to use one past paper question. Okay. So let's see. One. Okay. I think maybe we should have 3. Okay. Example A, we say, let's see, a 1050 or 10,000, 1,050 kilogram car with a velocity, or has a velocity of 2.65 meter per second north. The car hits the rear. Of a stationary truck. Right? And the bumpers lock together. All right, the velocity of the truck, or the velocity of the car truck, because they are locked together, the velocity of the car truck system immediately after the collision of the car truck system, what's happening with my writing? Immediately after the collision is 0.78 meters per second in knots. Calculate the mass of the truck. calculate the mass of the truck. Calculate the mass of the truck. Okay. Right. Now let's see. We will say for our solution, let me extract the data. Okay, let me wait for you guys to take the data. So the mass of the car, and okay, let me just do this for solutions. For mass solution and narrate it in full. We'll say the mass of the truck, let's call the truck A or 1, whichever you prefer, guys. The mass of the truck is 1050 kilograms, 1050 kilograms. It has a velocity of 2.6 meters north. Okay. So V sub AI is 2.65 meters north. 2.65 meters per second, north. And then they said, oh boy. And then they said that the car and the truck got stuck together. And oh boy. They said the car and the truck got stuck together. So let's wait for this guy to respond. I wonder why he's freezing now, but it's okay. Oh yeah, indeed he is freezing. All right. So okay, he's back. So the car and the truck got stuck together because their bumper locked together. Now the velocity of the car truck system immediately after collision is 0.78. So I'm just going to call it simply VF will be 0.78 meters per second north. Now something that you need to do after collision, both the truck and the car are stuck together. So our mass will be mass of A plus mass of B. So let's see. Now, to answer this question, first thing first, we will take north as positive. Okay? So north is positive. Please write positive in full. So the formula, MAVAI plus MPVBI is equal to MAVA final plus MPVB final. However, I don't want to substitute as yet. I want to remind you, remember, after the collision, the car and the truck got stuck together. So they move at the same velocity. So this will be M sub A plus M sub B. Right, M sub B. They move with the same velocity. Let's call it V sub. Now substituting, we said the mass of the car was 1050 kilograms. The velocity, initial velocity was 2.65 meters per second north. We said north is positive, so it'll be positive 2.65. The truck, we do not know its mass. Initially, it was 0. Let me see. Yes, initial velocity of the truck, because it was a stationary truck, its initial velocity was 0. So VB initial is 0. So it's 0. Now, mass of the car, we know it's 1050. I'm calling the car A. Mass of the truck is unknown. What is their final velocity? It's 0.78 meters per second north. So it will be positive. So even if you hadn't done this like this, it's still okay. By continuing with this, it was still going to work. Okay. So proceeding. 1050 times 2.65, let's see, will be 2,782.5 plus 0 is equal to 1050 times 0.78, 1050 times 0.78 8 would be 819 plus 0.78 m sub b, isn't it? This times this is 0.78 m sub b. All right. So 2782.5 minus 819 will be 1963. It'll be 1963.5, which is equal to 0.78 m sub b. This divided by 0.78 becomes 2517.31. All right. Therefore, mass of the truck is 2517.31 kilograms. I would have written kilograms as well here. I should have. It's okay. Right. So mass of the truck is 2517.31 kilograms. Okay. All right. Now, with this question, we somehow have to be careful because with this section, the formula and everything, we have to be careful of our calculations. We have to understand the question before we rush to answering it. Okay, it's very key that you understand the question because the questions can be tricky. So now let's move on to get the second question. Maybe let me choose a past paper. Okay, yeah, this is a past paper. Oh yeah. So this is a past paper. All right. So now let's see. I forgot the year. I think it was somewhere 2018 or 19. It's one of your June SC examinations, right? So let's see. A soccer ball. Okay, a soccer player kicks a ball of mass 0.45. So let's call it like we've been doing. We're going to call it M of A. I'm extracting my data. M of A is, or maybe let me duplicate this slide as well, because I'm still going to use it on the next page. Let me duplicate it. Where is it? Yeah, that there. Okay. So M of A is 0.45 kilograms. Okay, by they saying that it kicks the ball of mass 0.45 kilograms to the east, the ball travels horizontally at a velocity of, so initial velocity of A is 2 or 9 meters per second. Why am I saying 2? East. All right. So, so it travels along a straight line without touching the ground and enters a container main at rest. So VB initial is 0, as shown in the diagram below. The mass of the container is 0.20. Mass of the container is 0.20. Okay, cool. Now, proceeding, the ball is stuck in the container after the collision. So when they say stuck, this means after collision. This means after collision, the new mass will be, okay, after collision, the new mass, because they are stuck, they now moving as a unit. We will write our mass as a mass of A plus a mass of B, right? Okay, so after the container, after the ball is stuck in the container after the collision, the ball and the container now move together along a straight line towards the east. Ignore friction and rotational effects. It's okay. State the principle of conservation of linear momentum in winds. Remember, you can also state it in numbers or in letters. Sorry, mathematical expression of it in letters. All right. So this will be, what did we say? We said total linear momentum. We said it's total linear momentum of an isolated system isolated system is conserved. You recall, if you don't want to say is conserved, you can say remains constant. Alright, if you don't want to say is conserved, you can say remains constant. Now, they say calculate the magnitude of the velocity of the ball container system immediately after collision. It's okay. So 4.2, we will say, remember, I said to you, you can write this formula as MA VAI plus M B VBI is equal to MA VAI plus MB VBF, not I, right? But because these got stuck together, we're going to use it as MA VAI plus MB VBI is equal to MA plus MB multiplied by VN. Now, before you proceed, you need to state a direction you want to be positive. So I will say east is, I should get used to writing in full. East is positive. Okay, I will say east is positive. Okay, you can see they give you the cardinal points here, your compass is here, stuff. So you know east is this direction, west is that. Okay, north is up, south is down. Okay, so we said the mass of object A was 0.45. It was going east with 9 meters per second. The mass of object B was 0.20. It was at rest. 0.20, it was at rest, which is 0. They are extracted, yes, correct. Now, this will be 0.45 plus 0.20 multiplied by V sub n. 0.45 times 9 will be 0.45 times 9 will be 4.05, 4.05, 4.05. Anything multiplied by 0 is 0. And this will be 0.65 VF. 0.45 plus 0.20 is 0.65. Alright? Perfect. Now, we are basically saying the step that I'm writing is honestly not necessary because it's just going to be 4.045. So 4.045 divided by 0.65. What is our answer? Our answer is 6.23, right? Therefore, I will say our velocity is 6.23 meters per second. As you can see, it's positive velocity. So it's in which direction? It's east. So they moved east at 6.23 meters per second. Okay. They moved east at 6.23 meters per second. So 4.3, determined by means of a suitable calculation whether the collision between the ball and the container is elastic or inelastic. So what we are going to do here is this simply is. We will not do this question because it requires knowledge of elastic and inelastic collisions. So you don't have this yet. We are going to cover this in the next video. Okay, in the next video, we are going to cover this. So with that being said, let's go back and see if we have answered all the questions. So let's see if we have answered the questions we asked at first. So let's see. So we asked, imagine the collision of two objects with similar different momentums. We have somehow been able to look at them. We were able to derive the law of conservation of momentum. So we're able to find the mass of either one of them or their velocities if they are not given, or their velocity if they are not given. So we have done a Newton's third law of motion, and which led to the derivation of the law of conservation of linear momentum. right? We have done some examples as well. So I think we are, I think we are good to go. I think we are good to go. So with that being said, ours ends here. I will see you next time. And in the next video, we're going to look at collisions. So with that being said, it's a wrap and bye-bye.